Alrighty, hello and welcome back to Software Engineer Place. Back in Human Resource Machine today. Let's go ahead and jump right in. I've been at the company for 20 years now. Let's go ahead and jump up the left path here. So, looks like the name of this room is the Fibonacci Visitor, so I think we're going to be talking about the Fibonacci sequence in this problem, which is pretty common. Fibonacci is kind of an interesting sequence. Basically, it's a sequence where you start off with 1 and two ones, so 1, 1, and then the next number is the sum of the next two, or the previous two numbers in the sequence. So 1, 1, the sum of those two is 2, so the next number in the Fibonacci sequence is 2. Then you have 1 and 2 as the previous two numbers, so the next number is 3, and so on and so forth. It's a fun sequence. Very commonly it's taught in the core of computer science classes as an example of a function that can be calculated recursively. And the idea behind recursion is kind of taking a problem and breaking it down into smaller parts. And basically you just keep breaking down the problem into smaller parts until you get to the smallest part of the problem possible, and then you work your way back up. So the smallest part, what we would call the base case in recursion, and in the case of Fibonacci, the base case is if the number is equal to 1. So basically, if you give a recursive function for calculating Fibonacci, say 5, you pass it 5 as a parameter, it will work all the way back down until it passes itself a value of 1 as a parameter, and then it works its way all the way back. And I'll do an example of that in actual code here on screen in a second. But so let's talk a little bit about recursion specifically as it applies to the Fibonacci sequence. So I have fired up Visual Studio Community Edition here, and just created a template C# program. C# just being a programming language, one that I enjoy writing. And you've got your basic program structure. We talked about Hello World in an earlier video. This program is just a simple Hello World. If I run it, you'll see in the output window down here, and in the console window, Hello World. So that's pretty exciting. But let's jump right into the Fibonacci sequence. So we don't need any of this stuff. What we're going to do, though, is create a function, and it's going to be a recursive function. And we'll see what all that means here. But it's going to be a function that returns an integer. So we need to specify the return type, int, and we'll call it fib. Now, another important part is what parameter we're going to pass to it. So the way this function is typically written is to spit out the nth Fibonacci number, where n is the parameter. So let's pass it n as a parameter. N will be an integer, so we've called it int n there. We'll set up our curly braces, and you'll see that we've got a squiggle here because we have not yet specified a return value. Also, it's complaining about some naming conventions, because I guess they want your function name to start with a capital letter. So there are two parts of a recursive function. The most important part is what we call the base case, which is when it should stop recursing, calling itself, breaking the problem down into smaller parts. So in the case of the Fibonacci sequence, our base case is when the number is 1, because the first two numbers are 1. So we want to put an if statement in here, and we want to say if n is equal to 1, just so you know, in C#, 2 equals signs is the equality operator. Then if n is equal to 1, we want to just return 1. So the return keyword here just tells it to exit out of the function. And just to cover all of our bases, instead of equal to 1, let's go ahead and make it less than or equal to 1 in case n ever becomes 0. So that'll be our base case. So if n is 1 or 0 or any negative number somehow, shouldn't ever happen, but if it does, then we will return 1. However, if n is greater than 1, then we want to do the actual recursion. So we know, looking at our Fibonacci sequence, right, we have 1, 1, 2, 3, 5, 8, and so on and so forth. So if n is 1, those are going to be handled. So when we get to n is equal to 3 here, so it's the third number, so if n is 3, then what we want to do is come in here and we want to return the number before and the number 2 times before. So if we return n minus 1 and add it to the 2 numbers ago, put a semicolon to tell it that's the end of the line. So this will say return this function of n minus 1 and n minus 2. So if we step through this, we pass it a 2. So, I mean, technically, that's gonna, if we pass it a 3, let's step through there. Okay, so 3 will come in, and we will say, okay, return this function of, it'll come in and say return fib of 2 plus fib of 1. So if we then break this down, fib of 2 equals fib of 1 plus fib of 0. So both of these will return 1 because of our base case here. So fib of 2 is equal to 2. And then fib of 1 is going to be 1. So fib 1 equals 1. So we end up getting 2 plus 1, we end up getting 3. Which is the third number here. Well, technically it's the fourth number, but if that's the 0th number in the sequence, then... Anyway, console.writeLine fib of 3. And it does not like that because I need to make this static. Okay, now it's happy. So if we went through this, we should end up with it printing out the number 3. Lo and behold, 3. Which is pretty exciting, I know. But if we step through this, what I'll do is I'll make it print out the number that it's on here. So I'll print out console.writeLine n. We'll print out n, and then we'll be able to see a whole bunch of extra numbers, and the extra numbers are the recursive calls. So you'll see the number 1 a bunch of times. So yeah, we can break this down here. So 3 came in first. So then it called fib of n minus 1, which is 2. which then called fib of n minus 1, which is 1, which then called fib of n minus 1, which is 0. And then we had the fib of n minus 2, which, 3 minus 2 is 1. And then the final 3 there is this console.write line here. So you can see the way the compiler worked, the way this code was executed, is the n minus 1 part was always executed first. So 3 came in first, and then n was minus 1, which is 2. So then this n minus 1 happened again. We got 1. And then since n was less than or equal to 1, we returned a 1. And then we got a 0 in there from the fib of n minus 2 of this 2. So this 2 came in, and we got fib of n minus 2, which is 0, which then we returned a 1. And you can see that trying to look at it this way gets pretty confusing, but it's helpful to draw like a tree, and let's make the tree, fire up the tree here in everyone's favorite. We're firing up PowerPoint because everyone loves PowerPoint. And so we are going to break this down into the functions and the functions that get called. So this is n equals 3. So then when that gets called, center fib 3, n equals 3, that means that because n is greater than 1, to learn how to type, that means we call 2 functions. We call n minus 1 to 2, n equals 2, n is greater than 1, and we call fib of 1, n equals 1. So n is less than or equal to 1, which means we return 1. Okay, and then this one, because it is greater than 1, we do another recursive call on the 2. So we have minus 1 here, fib of 1, n is equal to 1, n is less than or equal to 1, fib of 1, fib of 0, n equals 0, n is less than or equal to 1, return 1. So, now, we connect all of these together. This guy calls that guy, and adds them together. This one calls that one, and that one, and calls them together. So, you can see the recursion is breaking it down into smaller parts, where the smallest part is always the base case, where n is 1 or 0. And then these get added up, so the return here, I'm going to add another box, make it green, is equal to sum, and that gets returned. So let's put in some green arrows to show the flow. Those come back in, make it a green arrow. And the sum of those is equal to 2, which then gets passed up to here. PowerPoint is definitely the best tool to do this in. And now we have another sum block here. So we have 2 coming in here, we have 1 here, so the sum there is 3. And here. in there. So then that gets returned to the original caller. And then if you're super compulsive, you want to get everything lined up and pretty. Okay, and this guy needs to move down like a couple pixels. Ah, there we go. Perfect. Beautiful. So, yes, the original call here, was Fibonacci, fib of 3, n was equal to 3, so then we called fib of n minus 1 over here. And over here, fib of n minus 2. And because this was the base case, triggered base case n less than or equal to 1. And it goes there. And then because this did not trigger the base case, then we have to do the recursive call again, which means we get fib of n minus 1 over here. Which does trigger the base case because now n is equal to 1. And we also had fib of n minus 2, which triggered the base case because n was less than or equal to 1. So what you might notice is that this is not going to be the most efficient way of calculating things. And the reason for that is you can see that we're calculating the same value very many times. This is a very small example. You can imagine if 3 was a bigger number, we would have a much larger branching tree, and we would have very many more calculations of the value of Fibonacci of 1 and Fibonacci of 0. All of these blue circles would get calculated multiple times, which is not necessarily, well, it's definitely not optimal in terms of time and memory usage. So there are a couple of different ways you can calculate the Fibonacci sequence. The first way is iteratively, using a for loop. So let's make a static private int fib iterative n. So basically, we want a for loop. We'll declare our for loop using the keyword for. So for int I is equal to 0, I less than n, I plus plus. So these parts of the for loop, first we declare our iterator, that's this first part. This is our stopping condition. It's kind of like the base case in recursion. And then this tells, this is how much to increase or decrease our iterator through the loop. So I plus plus. Plus plus means take the value of I and add 1 to it. Plus plus is just a shorthand way of saying plus 1, basically. So, I'm thinking this may not be the best way to do it. We may actually want to start with n and work our way down. So let's go ahead and do that. Just to show you a different way the for loop can be written. So we're declaring our iterator value of I equal to n. We're going to say we're going to do greater than or equal to 1. Or should we do 0? Let's do 1 and see what happens. And then I minus minus. So what we want to do is, let's declare just a counter variable equal to 0. So, well, actually, counter will equal n here. Will it? No. We'll have counter equal n inside the loop here. So, counter equals I plus I minus 1. And let's think if this is going to work here. We're going to get n. I will, let's say n was 3. 3 will come in, say 3 plus 2. No, it's not going to work. So we need to reconsider our logic. So I think probably the easiest way to do this, instead of trying to use n, we'll instead start the counter at 1, and we will in fact count up. So we'll say for int I equals 0, I less than n, I plus plus. What we will then do is say counter equals, well, let's see, we need, we need another number. So there are a couple ways we can do this. We can do it just by swapping numbers back and forth. Counter 2 also equals 1. I'm going to call these A and B because I don't want to type counter and counter 2 every time. So A is equal to A plus B. I'm missing a semicolon up here. And then we will get, we want to do a swap, basically. And we could get fancy and just basically using something that we call modular arithmetic, switch which number we're setting equal every time. That sounds kind of like a more elegant solution than declaring a temporary variable and doing a swap. So we will do that. We'll say if I mod 2 is equal to 0, we will make A the counter variable. Otherwise, we will make B the counter. And what that will do, just get rid of these extra curly braces. And then we want to return the value. So we want to return the greater of the two values. So return, if A is greater than B, return B, otherwise return A. Excuse me, I got that backwards. A, then B. So, okay. So this is well, let's just step through it and see what happens here. We get n in, so 3 would come in, we have 0, so we get, tell you what, here's what we're going to do. We're going to put a breakpoint in, and we're going to step through it, and see how it all works. So, we'll trigger our breakpoint. So the compiler is stopping here so we can see everything going on. So we have in our local window, we have the values of A and B and the value of n, and we've declared I, our iterator, to be 0. So as we step through here, now I is 0, I mod 2 is 0, so A will become A plus B. A is now 2. Now we're going to add 1 to I, so I becomes 1. We're going to come in here, and I mod 2 is 1. And the reason for that is the modular operator is basically the remainder of a division problem. So 1 divided by 2 is 0, remainder 1. So we're going to execute this else statement now, and B will become A plus B. So B will now become 3. Now we'll step through it again, and we will have I is equal to 2, so 2 divided by 2 is 0 with no remainder, or sorry, it's 1 with no remainder. Forgetting my basic math here, so we're going to execute this statement. A will become 2 plus 3, which is 5. And we have our last value stored in B, so we're just going to keep on going here. Now, we have 5 as our value. And this statement here is basically it's basically like writing an if statement in one line. So this is what we're evaluating, A greater than B. So if A is greater than B, return A, otherwise return B. So A is greater than B, so we're going to return 5 here. And we will now spit out a 5 to the console window. So you may have noticed a problem here, and that problem is that 5 is one number too far along in the sequence. And the reason for that is that we've already got our first number here. So we need to subtract 1 from n, basically. And we could do that in the for loop here. We could do it at the top by saying n minus minus, however we want to do it. But now, if I remove that breakpoint and step through it again, you'll see that it is now spitting out 3 as we would expect. So that's an iterative solution for the Fibonacci sequence. There are a couple other ways you can do it with arrays. If you declare an array and have the first 2 indices of that array equal to 1, and then you basically start at array position 2 and make it equal to the previous 2 array indices. There's also the entire idea of dynamic programming, and I'm not going to do an example of dynamic programming, but the way dynamic programming works, which is pretty cool and speeds up this whole process, is it basically stores the result of these blue circles as it calculates them, and then when it gets to another point where it would need to calculate that result, it says, have I already calculated the result for this problem? And if it has, then it just pulls that value that it's stored instead of going through all the math of calculating it again. So the advantage of that is, once you've calculated Fibonacci of 2, you never have to calculate it again, which means you cut off all of these extra branches and you don't have to do them as well. So a lot of gains to be had by doing dynamic programming. It gets a little bit more involved, and I don't really want to write that code on the fly here, so I won't get into it, but yeah, that's a quick rundown on the basics of recursion, especially as it applies to the Fibonacci sequence. Anyway, let's jump into implementing this in Human Resource Machine now. Now, I don't think there's any method for recursion in Human Resource Machine, so here's an example of the Fibonacci sequence as we talked about. So if the inbox is 10, we should output every number in the Fibonacci sequence that is less than 10. Okay, so here you can see the number. It starts off with 1, 1, as we talked about. Then the second number, or third number here, is the sum of the previous 2. Then this is the sum of the previous 2. Then 5, 8, and so on and so forth. So I think first, what we should do is start with getting the Fibonacci calculation correct. So they give us 0 here, which can also give us 1. So let's start off by just getting we need to start with the first two. So let's get 2 copies of 1 here. So we'll copy from 0. Let's call this A because it's going to be, and this one B. I think we're going to need a counter here as well. We may not. We may be able to use one of the existing numbers and do a swap, but it may be faster just to have the result to keep track of everything. So I'm going to copy that to the result for now, just so we have somewhere to add 1 to it. So that'll get us a 1. We're going to copy that to A, and we're going to copy that to B. So this should get us 1s in both A and B. Yep. Good deal. Okay. And now we're going to want to figure out how to get the Fibonacci exactly right. So we know that we need to add the 2 together to get the 3rd result. So if I pick up A, well, I already have B in my hand, so I think we don't actually need to copy it to B here. We're just going to add what's in A and copy that to B. So that should get us a 1 there, and then a 2. And then we should be able to keep adding. We want to store. Or here's what we're going to do. We're going to add what's in B, or have what's in A again, and then we're going to store in B, or store in A. So we basically just want to keep flip-flopping between the two spots. And I don't think we need this result. Do we need a 0? I'm not sure that we need a 0. Of course, the problem with that is that it will keep adding at each iteration through the loop unless we have our jump statement properly placed. So let's just make sure this is working. Get 1 there, 2 there, 3 there. And I realize that we're supposed to be outboxing the Fibonacci sequence as we go. So we're going to have to make a couple of tweaks here. First, we can outbox twice here. Copy to A, outbox, copy from A, outbox. That's the 2 1s out of the way. Let's make sure that's working. Okay. Copy from A again, add A, copy to B. Add A, copy to A, but we need outboxes along the way here. So after each add, I think we need an outbox. We want to store it first, move it to the outbox there. Do the add and store it in B, then we're going to outbox it. And then we need to pick up B, add A, copy to A, and outbox. Okay, so far so good. 1, 1, 2, 3. So now I think we have got the basic logic down that will let us loop. If I jump here up to here, that should print the Fibonacci sequence infinitely. Let's just make sure that's working. Excuse me as I take a drink there. That's not quite right. Let's step back and see what happened there. Okay, so the problem here is we're adding A after we copy. We need to add B every time. So these two need to be the same. Add B, copy to B, add A, copy to A. Let's make sure that works in this situation. We got one there. It's not going to work because there's nothing stored in B right now. So let's go ahead and copy to B as well. Just so we have 2 1s to start with. There may be things we can do to optimize this in the future, but for now, this I just want to get the basic logic outlined and working properly. Then we jump, copy from A, add B, copy to B. So you can see that it's flip-flopping. The highest number is always in the next, either A or B, and it changes every time through the loop, so... Okay, so this is good. You can see we are now outputting the Fibonacci sequence as we expect, so now what we can do is build in the logic to detect if the number we output is higher than our first number. So, what we can do... What I want to do is grab this number and store it somewhere. And then every time we go to the outbox, I want to compare it to that number and see if we get a negative number. Because that'll tell us that we've gotten a number that's higher than this. So, I'll call this our check. So... And just for the purpose of looping in the future, I'm going to copy from 0, which is actually going to be 1 from here on out. So I'm going to call this 1. Even though it starts out as a 0, we're making it 1 to begin with. Okay. So let's go ahead and inbox and store in check. And while we're at it, we want to have a jump with negative here and then a jump back up to there. So the negative, we have to do the check at this point. Well, actually, we have to do the check before. So if, well, we're gonna have to do it twice, but that is okay. So right as we're about to move to the outbox, we need to check to make sure that the number that we have in our hands is not greater than our initial number. So we subtract check, and oof, that's not going to work because that will always be negative. It'll be negative until we get... Oh, that... Okay, that's... If it is negative, that means we can continue the loop. But the main problem here... I mean, we really want it to be continue if negative. So that's what we're gonna do. We're gonna have this jump be out, and then this jump will jump back up to the top. Otherwise, we will be done. Let's make sure this works. So I'm not super sure. Okay, you're gonna initialize everything here. So let's... So we're into the loops now, so let's just make sure this all works. I'm a little bit concerned. We're gonna have to pick up our number again after we do this subtraction, because that's a negative 19. So we don't want to send that to the outbox, obviously. But we do, we can move the outbox down to here, but we want to add back the check. And we want to do the same thing here. Yes, so here's the problem. If we do the subtraction, if we subtract check down here, then if it's negative, we can't jump all the way up there quite yet because we need to add the check back, and then we can jump back up to here. Okay, and now this will be, we should be done at this point. So I think these technically could jump all the way back up to the top where we initialize everything. I think. Let's double check. Okay, so the first number, first of all, we're gonna get a 1, and then we're gonna initialize everything here. Okay, so far so good. Now we send the 1s out. And we start adding stuff, but where we get interested here is this part. So negative 17 is negative, so we can now add back our check and outbox it. And then continue doing the Fibonacci calculation. Get a 3, so we get a negative number, so we're going to add that back. And then outbox 3. So far so good. Now we continue our loop. 5, subtract 19 and get a negative number, so we're going to add that back and then outbox it. Then we are going to calculate the next number, which will be 8. That will be a negative 11, so we will add it back and outbox 8. And there we go, keep going, 13, we should get a negative 6 there. That is negative, so we'll add back, get a positive 13, outbox it. Now comes the interesting part, because when we add these together, we get a 21. So we subtract this, we're not going to get a negative number. So we should not outbox 21, and we should start all over again. So we're going to reinitialize everything, and hopefully the manager is happy with us. Yep, so far so good. And we will calculate Fibonacci all over again. Failed, so other possible inputs. Okay. Which inputs? 8 and 18. Okay, that's interesting. Let's go ahead and see why it fails on 8. Ah, I see why. Okay. So, yeah. Because 8 is one of the Fibonacci numbers, when we subtract our Fibonacci number 8 from it, we'll get 0 instead of a negative. So that's a problem, but it should be relatively easy to check. And the difference there is the difference between a less than and a less than or equal to. So the code currently works for a less than or equal to. Or rather, it doesn't. So what happened there? Basically, I mean, there's probably a better way to do this, but to account for those numbers where it's Fibonacci, this is going to make it a less than or equal to instead of just a less than, and yeah, so you can see they did specify that in the question, so it's my bad for not reading that super clearly. Up to but not exceeding, so that is a less than or equal to. So this should now work for all instances. It's probably not optimal, but it should work. We'll see how poorly we did when they give us our score at the end. How do we do? Okay. Alright, so we actually did okay on the speed. It's the size that's the problem. So in the next video we will work on cutting down the size of the program. Thank you very much for watching. This has been A Software Engineer Plays. If you like the content, please like, subscribe, tell a friend, tell 2 friends, tell 3 friends, tell 5 friends, tell 8 friends. You know, tell your favorite Fibonacci number of friends about the channel. I'd really appreciate it. Okay. That's it. I'm going to sign off. Thanks for watching. Bye.